pressure resistance and airflow and other gas laws of respiration. Okay, so simply put, the expansion and contraction of the thoracic cage does help produce airflow in and out of the lungs. Keep in mind that when you breathe in, the ribs go up and out, the diaphragm moves inferior, increasing the volume of the lung field. When you breathe out, the diaphragm moves superior and the rib cage goes down and in, forcing air out, decreasing the volume of the thoracic cage. So with Boyle's law, that is, the pressure of a given quantity of gas is inversely proportionate to its volume. Okay, so let's put that in layman's terms. All right, so if you have a so we're going to have two containers here and a kind of a plunger similar to a syringe where you're going to draw a fluid into the syringe via that rubber plunger. Okay, so if you take this plunger and move it like so, you're going to increase the volume. Okay, so there's going to be more space, so you're going to increase the volume and therefore decrease pressure. And as a result, you can fit more air into all of this volume. Okay, so if you take that plunger and you push and force the air out, you are decreasing the volume. So if you'll notice that there's not a lot of room here anymore, so you're decreasing the volume and therefore increasing the pressure. Okay, that's Boyle's law. Okay, let's look at Charles' law, which is the volume of a given quantity of gas is directly proportionate to the absolute temperature. Okay, what does this mean? In order to understand Charles' law, let's look at the four things that are responsible for breathing and gases and all that influence gases. Okay, they are pressure, temperature, volume, and the amount. Okay, so with gases, these are things that you're always going to be dealing with: pressure, temperature, volume, and amount. With Charles' law, it focuses on temperature and volume. All right, so let's draw our beakers again. And you have the plunger. Okay, similar to our syringe, right? So you can use the plunger to draw in fluid, which would increase the volume, and you can use the plunger to push out the fluid or air or gas by pressing on it, right? And that would push out the air or fluid. Okay, so Charles' law is going to focus on temperature and volume. Okay, so what you do is you put a heat source. Okay, so here's our flame underneath, or in this case, you're going to heat up. And so you're going to increase the temperature. And when you increase temperature, you are going to expand the gas. So you increase temperature, you increase gas expansion. All right, let's focus on this one here. We'll call this one number 1 and beaker number 2. So we're going to heat up the air and the gases that are currently in there. Okay, and as you heat it up, this plunger is actually going to move on its own. Okay, so then we can move the plunger that was here. So the dotted line represents that's where it was. We're heating it up, and because of the increase in temperature and the expansion of the volume, it now increases all of this surface area simply by increasing the temperature. So going back to Charles' law, the volume of a given quantity of gas is directly proportional to the temperature. Dalton's law is the total pressure of gas mixture is equal to the sum of the partial pressure of its individual gases. Let's look at Dalton's law in layman's terms. Okay, so first, know that gases are everywhere. Okay, so if you're out in a field and then there's a mountain and there's you, there are gases everywhere. Okay, now you don't really see them, okay, but these tiny little molecules of gases are everywhere. And so Dalton's law is also known as the law of partial pressure. Okay, we're going to focus on that word pressure. Okay, so a balloon analogy is I think, a good analogy. So here, this is going to represent a deflated balloon. Okay, so there's our deflated balloon. And then there's all of these gases that we can force into the balloon. And if you do that, you're going to take this balloon and you're going to expand it because of this pressure that gases exert. So now you have all these gases that are inside forcing the expansion of the skin of this balloon because of how much pressure that you're putting in that, using gases to exert that pressure. Okay, so we can force gas into tanks, gas tanks, and then we can also force gas into our lungs. Now, one of the things that happens is the more force that you put into this, the faster you're going to make these gas molecules bounce around off each other, exerting that partial pressure or force, in this case, against the skin of the balloon. So, in the lungs, okay, so in the lungs, the gases that we mostly deal with are nitrogen, oxygen, and carbon dioxide. Okay, these are the main gases, and each gas exerts a pressure within the lungs. Okay, so if the lungs are the balloon, okay, so there's the right and left lung. So if the lung is that balloon analogy and you are going to breathe air into the lungs, well, they are going to expand. Okay, so you get the expansion of the lungs, and this is the relationship between lung pressure, pleural pressure, and chest wall pressure. So Dalton's law with the partial pressure of gases is going to help the lungs expand. In Henry's law, this is at the air-water interface, the amount of gas that dissolves in water is determined by its solubility in water and its partial pressure in the air. Okay. In layman's terms, this is explaining how oxygen and carbon dioxide are exchanged between the alveoli and the blood. Okay, so using the alveoli gas exchange in fluid, let's put gas right here, and the liquid. Okay, and then there's a barrier like the alveoli barrier between. So there's the skin of the alveoli, right, which is made of simple squamous epithelium, and you've got the pulmonary capillaries, which has their own layer, also simple squamous epithelium. And so that's what this line represents, is essentially the skin of the alveoli and then the skin of the pulmonary capillaries. Okay, so we're going to have gas and we have liquid. Now, inside of your pulmonary capillaries, you have fluid, right? So the liquid is the blood. Okay, so we have a variety of different gases that are everywhere, right? So we're just going to keep it simple with carbon dioxide and oxygen. And of course, the liquid environment is going to be blood, and there is a lot of water that is going to be found in the blood. Okay, so this fluid or liquid environment. Okay, earlier we mentioned a partial pressure. Okay, so what is really meant by partial? Well, if you, so we have green circles, and now we're going to do black circles here. And what these circles represent are the gases. Okay, now just for the sake of simplicity, let's say that there are 15 black circles or gases and 15 green circles, which represents a different gas. Okay, so total pressure would be 30. Partial pressure would be 15. So if you're just looking at the black gases, that would be 15. If you're looking at the green gases, that would be 15. Okay, so let's say that we're going to focus on just the green gases. Then we're going to say the partial pressure is 15. Now, what does that translate into more realistic terms? Well, 1 ATM, or atmospheric pressure, which is the pressure gases exert at sea level, is also the same as 760 millimeters of mercury. Okay, so imagine a blood pressure cuff that is put on your arm, and most providers will pump up a blood pressure cuff to about 200 millimeters of mercury. Okay, so if you've ever had your blood pressure taken, and that blood pressure is squeezing down on your arm, that's pressure. And if that's 200 millimeters of mercury, that's a lot of pressure. As you know, that it's uncomfortable to have that done. Can you imagine 760, that blood pressure cuff squeezed to 760? Okay, that would really hurt. Okay, so using this formula here, we're dealing with 50%, right? So if total is 30, half of that is 15. So then we're going to take if we're just focusing, let's say, on the green gases, then that is 50% of the total pressure. So that's going to leave us at 380 millimeters of mercury. So in other words, the partial pressure that the green gases are exerting in this particular example is 380 millimeters of mercury. All right, so I kept the math simple by just saying there's 15 black gases and 15 green gases. Now, you could say that there are 20 green gases and 5 black gases. So then that changes your ratio. So I just did it to keep the math simple at 50%. Okay. Now, also keep in mind that the gases are also moving in all sorts of different directions, right? They're not stationary. Gases bounce off each other. They're moving around. And sometimes these gases will then drop down into, in this case, the pulmonary capillaries, so the alveoli, pulmonary capillaries, and so the gases will at times cross over from the alveoli into the bloodstream, or specifically the pulmonary capillaries in this case. That being said, if you do deep breathing and you're going to increase the partial pressure of gas, these things are going to bounce around even more, and you're going to force more into the bloodstream. Okay, and then likewise, you have carbon dioxide that also needs to leave the bloodstream, get put into the alveoli in the lungs, and eventually you're going to breathe that out. And you can increase this rate if you have increased temperature. So a warmer environment might help to increase this whole gas exchange. Okay, so that in hopefully a nutshell is Henry's law.